Medium-sized rings span 8 to 11 carbons in size. This lattice provides an optimal arrangement of atoms for minimal angular and torsional strain. Although the torsional strain can be higher than in smaller rings on average, it's not necessarily because of atom location, but just because there are more carbon-hydrogen bonds to deal with. We can see adamantane within it, and it's the arrangement that diamond adopts. If you can superimpose your ring upon this lattice, as we will see, it can offer a lower energy conformation than if you can't. So it will be a guide for us to use when discussing the conformations of these medium rings. Because of this, even numbers of rings, 6, 10, or 8, have lower strain than odd numbers of carbons, for example, 11 or 9. The even carbon size rings fall into two subcategories. 4n plus 2, for example 6 where n is 1, or 10 where n is 2. And 4n, for example 8 where n is 2. 4n plus 2 is a lower energy than 4n. In addition, the 4n rings conformation imposable upon the lattice isn't the optimal conformation of lowest energy. Now, cyclohexane isn't a medium-sized ring, but it's included here as it's the smallest ring that fits the lattice, and thus the smallest ring nearest to medium rings that follows the 4n plus 2. Plus, it's the ring with the lowest energy of all rings, making it a useful comparison. Here it is superimposed upon the lattice. Both representations are chair conformations. The left example obviously so, and the right one from that orientation less obviously so. But if you have a good grasp of the lattice arrangement, you can see it must be a chair conformation. Now, how about the 8-carbon ring of cyclooctane? It is 4n, and we can superimpose it upon the lattice. But as we anticipated, the ensuing conformation does not have the lowest possible energy. Here is the conformation off the lattice. It is called boat-boat, as two sets of two single bonds are orientated in a similar way to the boat conformation. This pattern is repeated further down the ring, again analogous to boat cyclohexane. The dilemma with cycloalkanes that superimpose upon the lattice that are larger than cyclohexane is that often the lattice unused by carbon-carbon bonds is taken up by hydrogens attached to the carbon ring, but two hydrogens each attached to carbons at different locations are superimposable on the same point on the lattice. Clearly, this is not possible, and the ring distorts from the lattice to prevent this, but there is still an elevated energy as a result. This is typical of transannular ring strain, a form of steric strain. Trans means across, and annular means ring, so strain across the ring. The boat-boat conformation has two such transannular strain interactions, marked in purple. This prohibitively raises the energy to a level such that the boat-boat conformation will not form. Instead, the repositioning of just one of the carbons from facing forward to facing back removes one of the transannular strain interactions, creating a conformation that is of significantly lower energy and is adopted by 89% of cyclooctanes. This is called a boat-chair conformation, as two sets of two single bonds are orientated in a similar way to the boat conformation in cyclohexane, and another two sets of two single bonds are orientated again analogous to a chair conformation in cyclohexane. Note, as predicted, the boat-chair conformation does not superimpose upon the lattice. Next, we will contemplate the conformations of Cyclodecane, C10. It is 4n plus 2, so we would expect the lowest energy conformation to be superimposable upon the lattice. Let's see what we get. First, this conformation fits on the lattice, but would require two hydrogens to be superimposed upon each other half a bond length from their respective carbons, as depicted here, or each hydrogen overlaps with the opposite carbon. However you put it, energetically, it isn't very pretty. So this is a warning. Just because it fits on the lattice doesn't mean it doesn't have prohibitively high transannular ring strain. Here are two ways to fit cyclodecane on the lattice. They are both the same conformation, seen from different directions. To help depict them, we can think of it as two fused boat conformation cyclohexanes, or alternatively, two cyclohexane chair conformations attached to each other, where a point on each is a hydrogen rather than a carbon. So that is there just to help you draw them. But those hydrogens do imply more transannular ring strains. Despite there being two such interactions, this conformation is the lowest energy conformation of cyclodecane. So what is it called? It is boat-chair boat. Let me show you why. Again, at one end of the ring, two sets of two single bonds are orientated in a similar way to the boat conformation in cyclohexane. And another two sets of two single bonds more towards the middle of the ring are orientated again analogous to a chair conformation. And the other end has two sets of two single bonds that are orientated in a similar way to a boat conformation. So when it comes to medium rings, we need to be aware that there is an elevated level of steric strain present in them.